On September 14th, 2017, at 12:59 in the afternoon Pacific time, a spacecraft that had spent 13 years orbiting Saturn took its final photographs. It had already been dying for weeks by that point, deliberately, on NASA's own orders, diving through the narrow gap between Saturn and its rings again and again in a sequence of orbits engineers had nicknamed the Grand Finale, gathering as much science as possible before its inevitable planned destruction. The next morning, September 15th, at 4:55 a.m. Pacific time, Cassini's signal reached Earth for the last time, then vanished as the spacecraft burned apart in Saturn's upper atmosphere, becoming, quite literally, a part of the planet it had spent over a decade studying. For years, everyone assumed that was the whole story, a beautiful, dramatic ending to one of the most successful missions in the history of planetary exploration. But buried in Cassini's very last measurements taken during those final daring dives through the rings was a piece of data that quietly contradicted something scientists thought they already understood about Saturn. And in February of 2026, a team of researchers finally figured out what that contradiction actually meant. Their answer involves a moon that no longer exists, a collision powerful enough to build the rings we see today, and a mystery about Saturn's largest moon, Titan, that Cassini itself first noticed but never lived long enough to solve. This is the real story of what Cassini's final measurements just revealed nearly a decade after the spacecraft itself went silent. I'm your host, and this is your channel. If you want the real science behind the biggest discoveries in space, subscribe now, because we're just getting started. To understand why this new research matters, you first have to understand what Cassini actually accomplished during its final weeks, because the grand finale wasn't just a dramatic send-off for the cameras. It was one of the most scientifically valuable phases of the entire 13-year mission. Beginning in April 2017, mission controllers steered Cassini through 22 increasingly daring orbits, threading the spacecraft through the narrow, roughly 1,200-mile gap between Saturn's cloud tops and the inner edge of its rings, territory no spacecraft had ever attempted to fly through before. It was a genuinely risky maneuver. Nobody knew for certain whether that gap was truly empty, or whether it contained ring particles large enough to seriously damage the spacecraft at the speeds Cassini was traveling. But the scientific payoff was worth the risk, because flying that close to Saturn let Cassini's instruments measure things about the planet that had never been directly measurable from any greater distance, including exactly how Saturn's mass is distributed inside itself, a property that directly controls the way the entire planet slowly wobbles in space over time, a phenomenon astronomers call precession. For decades before Cassini's final measurements came in, the leading model of how Saturn's rings became so visible from Earth relied on a specific, elegant explanation involving Neptune. Researchers believed Saturn's precession rate happened to closely match a specific orbital rhythm associated with Neptune, allowing the gravitational interaction between the two planets to gradually tilt Saturn over enormous timescales, tipping its rings toward an angle where they'd eventually become strikingly visible to observers here on Earth. It was a tidy, satisfying story, one that connected Saturn's most iconic visual feature to the gravitational influence of a planet 3 billion miles further out. Then Cassini's final gravity measurements came back, and that tidy story ran into a problem. The data revealed that Saturn's internal mass is actually concentrated more heavily toward its center than the earlier models had assumed. That might sound like a small technical correction, but it has an outsized effect on the specific physics involved, because that subtle shift in internal mass distribution changes Saturn's precession rate just enough that it no longer lines up with Neptune's orbital rhythm the way the older model required. The elegant Neptune explanation, in other words, quietly stopped working the moment Cassini's own final measurements were fully analyzed. To account for that mismatch, researchers at MIT and the University of California, Berkeley proposed something dramatic: that Saturn once had an additional moon, one that no longer exists today, and that this vanished moon had drifted close enough to Titan, Saturn's largest moon, to be flung away entirely during a close gravitational encounter, eventually breaking apart and forming the rings we see today. It was a genuinely compelling idea, offering a new explanation for both the precession mismatch and the surprisingly young age of Saturn's rings, estimated at only around 100 million years old, remarkably recent on a cosmic timescale, and itself one of Cassini's most surprising legacy discoveries. This is where a research team at the SETI Institute, led by planetary scientist Mattia Chuk, picked up the thread and took it somewhere nobody had previously considered. Working with colleagues, Chuk's team set out to actually test whether an extra moon migrating close to Saturn could plausibly have produced the rings the way the MIT and Berkeley researchers proposed. They built detailed computer simulations modeling exactly how such a moon would behave as it drifted inward towards Saturn under a variety of realistic starting conditions. And the simulations kept producing an outcome nobody was specifically looking for. In the vast majority of scenarios the team tested, the extra moon didn't simply get flung away and break apart into rings on its own. Instead, the most common outcome was a direct collision between that extra moon and Titan itself. That result opened up an entirely different, far more dramatic possible history for Saturn's largest moon, and the key piece of supporting evidence came from an entirely different, much smaller object in the Saturn system, Hyperion, a small, oddly shaped moon famous among planetary scientists for tumbling chaotically through space rather than rotating in the smooth, predictable way most moons do. Hyperion's orbit happens to be locked in a specific gravitational relationship with Titan's orbit, a genuine orbital resonance that has puzzled researchers for years. Chuck's team recognized something important about the age of that lock. Based on their analysis, the Titan-Hyperion orbital resonance appears to be relatively young, only a few 100 million years old, a time frame that lines up closely with when their simulations suggested the hypothetical extramoon would have disappeared from the system entirely. Chuck described the significance of this connection directly. Hyperion, he explained, the smallest of Saturn's major moons, provided the single most important clue about the true history of the entire system. In the simulations where the extramoon became unstable and eventually vanished, Hyperion itself was frequently lost as well, surviving intact only in a relatively small number of scenarios. Recognizing that the Titan-Hyperion lock is genuinely young, dating to roughly the same period when the extra moon disappeared from the models, led the team to a striking possibility, that Hyperion didn't simply survive whatever catastrophic event destroyed the extra moon. It may have actually formed as a direct result of that event. If the extra moon collided with and merged into Titan, the impact would almost certainly have scattered debris into orbits near Titan itself, and that is precisely the region of space where Hyperion currently orbits. The full model Chuck's team ultimately proposed goes even further than a simple collision, suggesting instead that Titan as we know it today may not be a single original moon at all, but rather the product of an ancient merger between two separate older moons. One of these, a large body the team refers to as Proto-Titan, would have been nearly as massive as the Titan we observe today. The other, a smaller companion the team calls Proto-Hyperion, would have been the object that ultimately collided with and merged into Proto-Titan, an event violent enough to fundamentally reshape the resulting moon and scatter debris that may have eventually become Hyperion itself. This model does something that had genuinely puzzled Cassini's own science team for years. It offers a real physical explanation for why Titan's surface shows remarkably few impact craters, a genuine anomaly for a moon its size and age, a massive merger event. Powerful enough to combine two separate moons into one would almost certainly have completely resurfaced whatever existed before, erasing the vast majority of any earlier crater record in the process. The model also accounts for something else Cassini observed but never fully explained. Titan's current orbit is slightly elongated, gradually becoming more circular over time, a pattern consistent with the disturbance you'd expect to see following a relatively recent dramatic merger event, rather than a moon that formed smoothly and gradually billions of years ago, the way most of Saturn's other moons appear to have done. Before any such collision, the researchers propose, Proto-Titan may have actually resembled Callisto, one of Jupiter's large moons, an old, heavily cratered world with no atmosphere at all, a stark contrast to the thick, hazy, nitrogen-rich atmosphere Titan displays today, an atmosphere that a violent merger event could plausibly have helped generate or dramatically reshape. The team's simulations produced one additional finding that connects to yet another long-standing mystery in the Saturn system. Before it was ultimately destroyed, the hypothetical Proto-Hyperion object may have gravitationally disturbed the orbit of Iapetus, one of Saturn's other major moons, a moon whose unusually tilted orbit has puzzled astronomers for years without a fully satisfying explanation. If confirmed, this same underlying event might end up explaining two separate, previously unconnected mysteries about the Saturn system simultaneously. Then there's the question of how all of this actually connects back to Saturn's rings themselves, the specific mystery that started this entire chain of research. More than a decade ago, some of the same SETI Institute researchers now involved in this study had proposed that Saturn's rings originated from debris created when several medium-sized moons, positioned closer to Saturn than Titan, collided with each other in a separate, distinct event. Later, researchers at the University of Edinburgh and NASA's Ames Research Center ran their own independent simulations, supporting this general idea, showing that while most debris from such collisions would eventually clump back together into new moons over time, a meaningful portion would instead get scattered inward toward Saturn, remaining there as the rings we observe today. The open question had always been what originally triggered those inner moon collisions in the first place. Earlier researchers had proposed the sun's own gravitational influence as the likely trigger. Chuck's new research proposes a different, more specific chain of events instead, that Titan's merger, the very collision that may have created Titan and Hyperion as we know them today, is what actually set this entire secondary process in motion. As Titan's orbit gradually shifted and migrated outward in the aftermath of its own merger, it would have periodically created specific orbital resonances with those closer, medium-sized inner moons, a configuration where gravitational interactions become significantly stronger due to simple repeating fractions between orbital periods. When those resonances occurred, the inner moons could have been pushed into more elongated, unstable orbits, dramatically increasing the odds that they would eventually collide with each other, generating exactly the kind of debris that later became Saturn's rings. The precise timing remains uncertain, but this second wave of destruction would necessarily have occurred sometime after Titan's own merger, a sequence of events that lines up consistently with the current estimate that Saturn's rings are only around 100 million years old. It's important to be honest about where this research currently stands, because that honesty is exactly what makes it credible, rather than exaggerated. This is a genuinely compelling, carefully modeled scientific hypothesis, accepted for publication in the peer-reviewed Planetary Science Journal, built on real gravitational simulations and real data from Cassini's own final measurements. It is not yet a confirmed fact about the history of the Saturn system. The research team itself has pointed toward a specific future opportunity that could provide much stronger, more direct evidence one way or the other. NASA's Dragonfly mission, a nuclear-powered rotorcraft currently scheduled to arrive at Titan in 2034, will study the moon's surface, geology and chemistry in unprecedented detail, directly on the ground rather than from orbit. If Dragonfly finds physical evidence of large-scale surface resurfacing or other geological signatures consistent with a massive collision occurring roughly 500 million years ago, it would provide real, direct support for the idea that Titan was fundamentally shaped by a dramatic ancient merger, rather than forming smoothly and gradually the way most other large moons in our solar system appear to have. So here is where this genuinely leaves things, honestly, based entirely on published, peer-reviewed research. A spacecraft that transmitted its final signal back to Earth on September 15th, 2017, took measurements during its very last, most daring orbits that scientists initially had no reason to suspect would upend a long-standing, elegant explanation for one of Saturn's most iconic features. Years of careful follow-up analysis eventually revealed a subtle mismatch in Saturn's internal structure, one that pointed toward a vanished moon, a violent ancient collision that may have created Titan itself as we know it today, and a connected secondary collision event among Saturn's inner moons that may have ultimately produced the rings that make this planet instantly recognizable to anyone who has ever looked through a telescope. Cassini's mission ended in 2017, but the data it gathered during its final, riskiest weeks in orbit is still, right now in 2026, actively rewriting our understanding of how an entire planetary system came to look the way it does. That is not manufactured drama. That is the genuine, ongoing legacy of a spacecraft that kept teaching us new things about Saturn years after it had already burned apart inside the planet's own atmosphere. If this kind of story is what you come here for, one grounded in exactly what scientists have actually measured and modeled, rather than exaggeration, hit subscribe and turn on notifications, because there's a lot more of Saturn's history left to uncover. Drop a comment telling me whether you think Dragonfly will find evidence of Titan's violent past when it arrives in 2034, and share this with someone who still thinks Cassini's story ended the moment it went silent.